we are talking about motion with constant acceleration, and we've written down constant acceleration kinematic equations, and we've justified why we don't bother with jerk, the time rate of change of acceleration, snap, crackle, pop, the next three derivatives after that, because anything can change. But we said that constant acceleration is pretty common situation to deal with. And one very common place where we deal with constant acceleration that we haven't talked about yet is free fall. That's things falling near the surface of the Earth, things that are falling in the Earth's gravitational field. So what I want to do next is talk a little bit about free fall and at what acceleration do things fall near the surface of the Earth. Aristotle in about 300 BCE said that things fall at different rates. Can't remember the word he used exactly, but things fall relative to their nature. So, you might think larger things fall faster than a smaller thing. That's not an uncommon thought. It wasn't until 2,000 years later that Galileo came along, 1600 CE, that's the modern equivalent of AD, CE, said that everything accelerates at the same rate independent of mass. Wait. Aristotle said 2,000 years earlier that everything falls at different rates relative to their nature. And it took 2,000 years for Galileo to come along, do some experiments dropping things off the Leaning Tower of Pisa, and say that everything falls at the same rate. That's when we say the same rate, we mean the same rate of acceleration. So who was right? Not sure that it is always clear. So let's do some experiments. So Aristotle studied at Plato's Academy, which is where I am today. And remember what he said was that different things fall at different rates relative to their nature. So what I'm showing here is dropping a book and a piece of paper together, and you can see that they actually do indeed fall at different rates and hit the floor at different times. So maybe Aristotle was right. So now I visit Galileo in the Leaning Tower of Pisa, and I drop the two ping pong balls like he did, and listen, you can hear them hit at the same rate. Now those are actually two different objects this third time, two different mass objects. Now two really different mass objects, one very heavy metal ball and a ping pong ball. Drop them at the same time from the same height, and you can hear that they hit the ground at the same time. Listen carefully as they fall. Same time, same height, in the Earth's gravitational field. And you only hear one bang. You can't hear them both hit because they both hit at the same time. So maybe things with different mass do fall at the same rate. Well, what about different size? Here's an apple and a ping pong ball, and they appear to fall at the same rate. Here's the world and a ping pong ball. Aha! Now what about that? The world looks like it falls a little slower, or I'm letting go of it a little late, but I think it's falling a little slower. So who's right, Aristotle or Galileo? Well, here's Aristotle's experiment again, the paper and the book. And, well, maybe Aristotle's right. So who's right? Well, let me try a different experiment. Let me put the paper on top of the book. Oh, interesting. Look at that. They fall at the same rate. That's just a slow motion version. So what do we conclude from our experiments with Aristotle and Galileo? Well, we were able to see two different situations where objects of different mass fell at different rates and objects of different mass fell at the same rate. So who was right, Aristotle or Galileo? And the answer is, I hope that you've thought about it, and I hope that you've tried to come up with an answer, but the answer is that they were both right. They were both right. But because they were talking about different situations, and certainly Galileo understood that they were talking about different situations. Aristotle said everything falls at different rate relative to their nature, and Aristotle was correct. Galileo said something different. Galileo said everything falls at the same rate in the absence of all other forces other than the Earth's gravitational field. So in the absence of all other forces, everything falls at the same rate. If there are other forces, what other forces might there be? What is a typical force that is exerted on something that's falling through the air? Right? Air resistance, friction. If you can reduce the friction, if you can get rid of the friction, then Galileo concluded that everything falls at the same rate due to the acceleration due to gravity. Now that's still a surprise, right? It's still a surprise that everything falls at the same rate. And most people naively still think that heavy things fall faster than light things, and that is simply not true, and you've got to accept that. In the absence of air resistance, everything falls at the same rate. And what do we mean again? Same rate of acceleration. If you drop them from the same height at the same time, they will fall at the same speed per unit time, and they will reach the ground at the same time. Regardless of their mass, it's air resistance that will slow down things with less density, typically less density. It has to do with shape as well, but density, and therefore in most cases less mass maybe. So what is that rate? Most of you have heard that rate at some point in your life. But we can actually do a very simple experiment. We can drop an object, we can time it, we can see how long it takes to fall, and we can calculate it from our constant acceleration equations. And you can drop a ping pong ball, you can drop a heavy steel ball, you can drop a car. And all of them, if they're not impacted much by other forces such as air resistance, all of them are going to fall at the same rate. What is that rate? Let's go ahead and do a quick experiment. Here I show myself dropping the two ping pong balls, but graphing the position versus time. We've got this great software that allows us to plot the position versus time on the video, and then it turns it into a graph. And here's your graph. So I've plotted the position versus time, and actually the software, I mean, you could do this mathematically, but it turns it into a velocity versus time curve. And what happens when you have a velocity versus time curve with a constant slope? It means that you've got constant acceleration. Here's my velocity versus time curve. It's a constant acceleration, and what's the value? It's minus 9.8 meters per second squared.